Hello. Here we will have an outline of a proof for quadratic reciprocity. Original proofs were due to Gauss, but here we will follow ideas of Zolotarev, Yegor Ivanovich Zolotarev. This is a particularly concise proof, and it uses a little bit of group theory, but yeah, still just enough to be very short. Just to remind what I was proving, it's the following relation on Legendre symbols. If we have two odd primes, so P and Q are odd primes, then Legendre symbol for P modulo Q times Legendre symbol for Q modulo P is equal to the negative 1 to the power P minus 1 times Q minus 1 over 4. So the idea due to Zolotarev is to interpret each of those signs as a sign of a certain permutation. And the permutation which we're going to use will come from three bijections between the sets. So let's introduce a short notation for the set of n elements, this square brackets around n, and we will think of elements starting from 0. Natural numbers going from 0 to n minus 1. So then we will use three bijections, row numbering, diagonal numbering, column numbering, and each numbering will be numbering elements in the product of two sets. So P, that prime P we chose, Q are the sides of the sets which we've used to form the Cartesian product, and then of course the cardinality of that is P times Q, and we can at least do it in three ways. Of course we can do it in P times Q factorial ways, but we will choose three special ways of identifying this set of length P times Q and the Cartesian product of the sets of size P and Q correspondingly. So just to illustrate, let me choose P to be, say, 5 and Q to be 3. Let me show on this choice what are the numberings in each of those bijections. Bijection with this sequence is just a numbering of, say, positions in the 3 by 5 rectangle. So I'll have to do it for the row, the diagonal, and the column bijections. And the row will just do what it suggests by its name, so it's not just numbering along the first row, and the zeroth row starts from the bottom, so that is following Cartesian coordinate system. That will be 0, that will be numbered 1, 2, 3, 4, then we'll have to wrap back to here, so 5, and then 6, 7, 8, 9, 10, 11, 12, 13, 14. Here we will go diagonally, starting again from this corner, so 0, 1, 2, we'll run out of our rectangle. But the rule now is we have to identify this horizontal side with this horizontal side, so just glue it into the cylinder. So that position which 3 wants to be in now identifies with this. So we have 3, and then we continue diagonally 4. Now we're here, and that is to be identified now along the horizontal edges. So these two are glued together as well. And this is here. So that is 5. Then we go out again 6, but 6 has to be here. 7, 8, 9 is in here, but 9 is now in here. Then 10 here, 11, 12 jumps to here, 13 and 14. So that is a diagonal numbering, and that is a consequence that is equivalent to Chinese remainder theorem, that since P and Q are co-prime, they are different dot primes, we won't have any gaps and we won't have any overlaps in this numbering system. So the last one, as its name suggests, is numbering along columns. Start with 0 here as usual, and then go up 1, 2, then move to the next column 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and the last 14. So we can really write them down in the formalic way. The row formula for a number in this list is as follows. Just need to write this number according to Euclid as some multiple of p plus a remainder. And then we will use the remainder to so the remainder will be modular p, which is this long side, and that will be used as the column position. So the column position is in here, and then A will be used as the height, as the elevation. So I'll have to flip them up. And let me just double check that everything is working as it should. So starting with 0, 0 is represented by 0 multiple and 0 remainder. So the coordinates are 0, 0, it's here. Then 1 is still 0 elevation, and then 1 along the x-axis. So that is 1, 0, that is in here. And then 2 all the way up to 4, and then when we reach 5, so 5 is our P, and 5 becomes recorded as 1 here and 0 here. So we have now we have 0 x coordinate, and then we have 1 y coordinate. So that is correct. Now let's look what D does to x. Well, maybe we'll just postpone it. We'll just do the column first, and then we will write the answer for D, because we will just need a certain notation which is natural for the column labeling. In the column labeling, we are dividing as for the row, but we're dividing by Q. So what I call them C, Q plus D. And then again, I will need to record them as my coordinates. So which one comes first? D is going to be for the first round before I reach Q. It's going to measure my elevation. So D is going to be here, and C is going to be the column number. So that's a formula for this numbering, and then the D formula will really be the function we used in the Chinese remainder theorem, which is just taking remainders modular P and Q. So remainder modular P is in here, remainder modular Q is in here. So this B comes as x coordinate as before, this D comes as y coordinate as before. So that is the rule of computing these functions, and they're bijective functions. So these two are bijective functions for any P and Q, and this is again by Chinese remainder we made the theorem, is bijective because P and Q are coprime. And now for the proof. So the proof will come from basically two facts. That the first ingredient in the formula, the Legendre symbol for P modulo Q, is going to be a sign of a certain permutation. So the permutation is going to be, well, take this row bijection and then go back with the diagonal bijection, and that will be permutation of P times Q elements and compute its sign. So going first with row and then following it with the inverse of diagonal. Then Q, Legendre symbol modulo P, is similarly the sign of going first with diagonal and coming back with the inverse of column. So I'm going with diagonal, labeling, and then going back with the inverse of column. So if we compose these two permutations, just forget about signs and look at those permutations, and if we compose them, then the composition, if we compose them this first and then followed by that, then the composition will be so C inverse D following D inverse R. So the composition will be just with D cancelling out, C inverse following R. So we now go with the row bijection and return with the column bijection. And that sign is on the right. So these three statements, really, these two come for the same price. These two statements are the ingredients in the proof. And that will be discussed somewhere else in the combinatorics video concerning signs. That is what we're going to prove. That is known as Zolotarev lemma. But yeah, let's look into it. So we are to compute, say, this sign. We are to compute the sign of this permutation. So we go with diagonal, and then we return back with the inverse to column labeling. What I'm going to do, computing this sign, I'm going to reverse the order and use the fact that the sign will not change. So now I'm starting in here and I'm going with inverse of diagonal. And should I go with inverse of diagonal? Maybe no, maybe I should go with inverse of the column and go back with diagonal. So let me try this. I go with inverse of column and then return with diagonal. So I'm claiming that the signs of this permutation which operates on the product and this permutation which operates on just the set of length of size P times Q are going to be the same, and then this is going to be easier to deal with. So let's look what this map is doing. We are starting with let me start here. Starting with column, inverse labeling, and then followed by diagonal. So when we do column inverse labeling, so we start with say C and D, and then what we really create, the inverse to column is actually easy. It's just this formula. It's that element here. So we just have to use the coordinates in the rectangle to compute the actual number. And then the diagonal labeling is nothing but reduction modular P and Q. So when we reduce modular P, we just get the reduction modulo p of this. We'll just write it as the remainder modulo p in the standard range. When we take the remainder modulo q, well, that formula is really good for taking the remainder modulo q, because that will be just this d. And if we look now at what it does to a pair CD, it doesn't change the second coordinate, it only just changes the first. So the sign of this permutation is just the sign of the permutation here, but it will be really repeated that many times as the cardinality of the set Q, but that is not going to change the sign because the multiple is odd. So the sign will be just the sign of this operation. So that will be now, because of this computation, the sign of a certain function. I'll call this function, should I call it u. So the function u now operates only on the first coordinate. The first coordinate I can now think of as the set of equivalence congruence classes modulo p, and the formula using the full arithmetic in here will be just, well, here's my x now, multiply x with q and shifted by d. So q is fixed, d is varying, but we're going to see that d is not going to affect the sign as well. So that is what we now have to investigate, the sign of this map. Let's break this operation into two. So let's think of u as the composition of two operations, of two permutations. And the first, just according to the formula, will scale our input by q. Let's take x and scale it by q. And let's call it s. So that will be s of x. And then the second one, which we call t, will be starting with anything and shifting it by d. So that is t of y. And of course the sign as for the composition will be the product of signs. Let's start with the second. We are shifting by 1. Oh, sorry, we are shifting by d, whatever d is. But that is an iteration of shifts by 1. So let's see what is the sign of this permutation of the remainders when we just shift everything by 1. Well, you can imagine that that is a cyclic permutation, so the sign is going to be -1 to the length of the cycle, which is p minus 1. And since p is odd, that is going to be +1. But now we are shifting by d, so that is iterating the shift by 1 d times, and that will be this power, still +1, because p is odd. So that is not going to bother us. Let's look at the sign of s. So now we're multiplying something by q. Multiplying something by q in the set of remainders modulo p. Well, 0 is going to be fixed, so really the sign is controlled by the sign of permutation. So the sign of s is really the same as the sign of its restriction to the non-zero remainders. And as such, it is going to be a permutation of p minus 1 elements, again given by multiplication by q. So that links with the group theory scheme. Let me write this scheme now. So I have my group of non-zero integers modulo p, and by Kelly's theorem I can think of them as permutations. So looking at how each element operates on the rest, I could record this effect and see them as permutations of p minus 1 elements, as many as group elements. So each element will be interpreted as a permutation of all the group elements. And then I could compose this with the sign homomorphism to just compute the sign. So that's what I'm supposed to do. And the claim is that this homomorphism is going to be non-trivial, and there's only one non-trivial homomorphism, and that has to be the Legendre symbol. So hence the answer here. Why is that? Well, because the group structure of this group is cyclic. It's a cyclic group of order p minus 1. So I'm just repeating the same diagram, the same sequence. So the key fact which I used is that this homomorphism is non-trivial, and there's only one such, which is the Legendre symbol. So that homomorphism is non-trivial because we could see in an abstract cyclic group what happens. So we take a cyclic group, it is generated by one element, so generated G, and we look at the multiplication of G on the rest, so all the powers, and that in terms of the powers will be shifted by 1, and that is a cycle of length p minus 1, and its sign is the minus 1 to the power of p minus 2, which is negative 1. So the homomorphism is non-trivial on the generator, so it is non-trivial, so it is Legendre symbol. So that's the kind of short group theoretical argument justifying this, and that is totally identical. It will be just operating on the second coordinate instead of the first. And yeah, we are done modular this result and using some group theory. So that is it. See you later.